Hello, my name is Felipe Saavedra. I'm a graduate research assistant in the Department of Civil Engineering at the University of Maine. My advisor is Dr. Roberto Lopez Anido. I work at the Advanced Structures and Composites Center for the Transportation Infrastructure Durability Center, or known as TIDC. My research work is the durability of large-scale 3D printed materials for transportation infrastructure. I would like to start with the motivation for this research work. The aging and deterioration of highway culverts across the nation requires rehabilitation methods. We can see this on the news every day. Like, there's always problems with culverts. Some highways get closed during several weeks because problem with highway culverts. And large-scale 3D printing offers a cost-effective solution with customized geometries for the existing culverts. As an introduction, accelerated testing or accelerated conditioning, according to Nelson et al., consists of a variety of test methods for shortening the life of products or hastening the degradation of their performance. Also, from the point of view of materials and structures in buildings and civil engineering, is the structure's ability to remain fit for purpose during its design working life. The materials selected for my research work are wood fiber polylactic acid, or as known as WFPLA, wood fiber amorphous polylactic acid, or as known as WFAPLA, and carbon fiber ABS. This research work studies the durability of large-scale 3D printed materials under moisture conditioning and freeze-thaw cycling. This is for wood flour PLA and wood flour APLA, and also for carbon fiber ABS, this material will be exposed to a cycle of UV exposure. Large-scale 3D printing is used for precast concrete formworks and for highway culvert diffusers rehabilitation. It is important to understand how these materials are going to behave under specific site conditions and to contribute to advancing the design of these materials for structural engineering. The objectives of this work are to characterize the effects of environmental exposure or mechanical properties of 3D printed polymer composite materials and implement material capacity reduction factors to account for environmental exposure in the structural design of 3D printed polymer composites. The research questions for this work are: how does moisture conditioning affect the hydromechanical response of large-scale 3D printed materials? Are flexural modulus and flexural strength dependent on specimen dimensions? Are flexural modulus and flexural strength dependent on the printing direction? And are there any differences in the hydromechanical response between machine and as-printed test specimens? And the last question is how to select 3D printed materials based on site environmental conditions. Diving into the research methods, flexural properties were selected to assess the durability of the large-scale 3D printed polymer composite materials. The ASTM D7264 was the standard selected using procedure B for 4-point bending. This test was selected because the central region of the beam is subjected to poor bending without shear. And also, like, flexure does not require whipping or tabbing like specimen intention. And with these materials in large scale, sometimes it's really hard to achieve tabbing or grabbing the specimen for testing. And flexural modulus and flexural strength were computed from the load cell and non-contact digital image correlation strains. Experimental data is used to determine residual properties and environmental exposure. 3 environmental exposure conditions were adopted. The first one is moisture conditioning following ASTM D5229, freeze-thaw cycling following ASTM D7031, and simulated weathering based on ultraviolet and condensation cycles following ASTM G154. Now, a discussion of the results. After the environmental exposures, 2 factors are defined, called C sub F and C sub E, to account for the retention of flexural strength and flexural modulus, respectively. The superscript I represents the exposure, M is for moisture conditioning, and F is for freeze-thaw cycling. Moisture conditioning, starting with the first conditioning that was implemented for wood flour APLA, this was the material with the highest moisture content, and carbon fiber ABS was the material with the lowest moisture content. If we look at figure 1, we can tell that carbon fiber ABS was less than 2%, and wood flour APLA was almost 10% moisture content. So there is a huge difference between these materials. Looking at the coefficient of moisture expansion, this one is affected by the dimension of the specimen's direction and surface finishing. Looking at the retention factors for wood flour APLA, the retention factors for a printed specimen was 0.31 and 0.67 for flexural modulus, for flexural strength and flexural modulus respectively. And for machine specimens, it was 0.49 and 0.56. For carbon fiber ABS, for flexural strength, the coefficient was 0.55. And for the flexural modulus, it was 0.85. Moving on to freeze-thaw cycling, wood flour APLA and carbon fiber ABS had no significant impact on their material properties, on their mechanical properties. And wood flour PLA has a retention factor for flexural modulus of 0.87. This is for as printed specimens. In the case for machine specimen, for flexural strength, this retention factor was 0.79, and for flexural modulus, it was 0.55. Moving on to UV exposure, after carbon fiber ABS is exposed to a cycle of UV light and condensation, damage can be noticed on the surface of the material, showing discoloration and material loss on the surface is exposed. And contact angle measurement shows that the surface of the material tends to be more water absorbent in early exposures. This is talking about the first 500 hours of the exposure, and less water absorbent in prolonged exposure. This was checked at the end of the conditioning for 2000 hours. The sustainability statement for this work is that all thermoplastic composite materials investigated can be recycled and reused for 3D printing other products. 2 of the materials have both bio-based polymers and reinforcing fibers. This is the case for wood flour PLA and wood flour APLA. Now, I would like to discuss conclusions and recommendations. First, the surface finishing impacts the material properties, showing that wood flour PLA and wood flour APLA flexural properties are 23 and 16% higher for machine specimens when they are compared to as printed specimens. The hydromechanical response evaluated by the coefficient of moisture expansion depends on the dimension of the specimen, direction, and surface finishing. In high moisture and water content environments, research findings show that carbon fiber ABS is a material that retains the lowest moisture content, equal to 1.35%, compared to 7.74% for wood flour PLA and 9.23% for wood flour APLA. Moisture degrades material properties. The retention factor for flexural modulus and flexural strain are 0.31 and 0.56 for wood flour APLA, and for carbon fiber ABS, these factors are 0.55 and 0.85 respectively. For freeze-thaw cycling, this conditioning only affected and damaged wood flour PLA, degrading material properties. The retention factor for flexural modulus and flexural strength were 0.79 and 0.55 respectively. In environments subjected to freeze-thaw cycle, research findings show that wood flour APLA and carbon fiber ABS have no significant impact on its materials properties, and a change in surface roughness and contact angle is observed in carbon fiber ABS after UV light and condensation exposure. This should be accounted for if this material is used in environments like the cycle exposure used in this research work. This is to avoid, and also to avoid this, it is recommended to research protective coatings. The future work of my research involves finalizing data analysis on the specimens under moisture conditioning for all the materials and the characterization of environmental effects, along with the computation of material capacity reduction factors for environmental exposure, and recommendations for the structural design of 3D printed parts for transportation application will be drafted. Also, something I would like to mention that my research is moving towards into. With my work, I was able to obtain the baseline flexural material properties. In this case, are flexural modulus and flexural strength. And then in case we have the exposed flexural material properties. With this, we can obtain this retention factor that I mentioned before, and we can obtain these factors for each conditioning, in this case, moisture or freeze-thaw cycle. So then the exposed properties are gonna be the baseline property multiplied by these factors. This is the end of my presentation. I will be more than happy to answer any questions related with this research. Thank you.